In this video, I'm going to be showing you how to use PLS-DA in PLS Toolbox. Now, a lot of what we're going to do is going to be the exact same as what we did in the PCA video, so I'm going to skip a lot of the basics. Just make sure that you're connected to Carlton's VPN first. So I'm going to be using this Lysate Nov 2017T data again, but this time instead of looking at donor 17, I'm going to look at donor 12. So since PLS-DA is actually used for discrimination, we are going to grab the train and test data from the pre-processing as well. So I'm going to call the prep set function, import the data. I'm going to choose donor 12, doses 0 and 5. I want all the serial numbers, and I'm going to apply all the same pre-processing as last time. Okay, I'm going to run the function, or the script rather. Now that it's done, we'll see in the workspace we have all our variables. In the all variable, we have all of our pre-processed spectra, so all of the 12, donor 12, 0 gray, and 5 gray spectra. And then in these other variables called train and test, we have 70% of the data in the train variable. So here we have the 0 gray and 5 gray again, but just 70% out of all of them. And then in the test variable, we have even fewer spectra, and this is 30% of the all variable, pretty much. So to open up the PLSDA workstation, you can just type in PLSDA in the command window. You could also go through the browse menu, as we saw in the previous video, but just typing in PLSDA is the fastest. So the PLSDA analysis window pops up, and it looks practically identical to the one from PCA. So first thing we want to do is import the data. So I'm going to go to the X block. And instead of just loading data in the X block this time, I'm actually going to load X and Y. So since this is a supervised form of machine learning, we're actually going to be telling PLSDA what class each spectrum falls into. And what it's going to try to do is it's going to try to separate the spectra based on that class. Whereas in PCA, we did specify a class, but it wasn't used in the calculation of the PCA model. So in the Y block is actually where the class data goes into. So I'm going to click Load X and Y. This load window pops up. So since we're training the model, I'm actually going to select the train variable here, double click on that for the X block, and then this Y block load window pops up, and I'm going to choose train again, and you'll see why in a second. What we're going to do is open up the edit data menu for the X block. The dataset editor pops up. And similarly to last time, I'm going to select the second column and use as class. Hit OK, and then select the first two columns and exclude. We don't care about the donor ID or serial number when creating the PLSDA model. We just want the Raman intensities. So I'll close out of that, go to the Y block, hit edit as well. And this time, all we want to include is the class which each spectrum belongs into. So the class would be corresponding to this second column because we're trying to separate based on dose. So class 1 is going to be the 0 gray and class 6 is going to be the 5 gray. So to do that, we just right click on the column and include only selected. So that should gray out everything else. All right, so once that's done, we just X out of that. For pre-processing on both X and Y block, we just choose mean centering. And then we hit the green button to create the model. Once the model is created, we could see all of our latent variables down in this window here. You can think of these like the principal components, but instead of being ordered based on how much variance in the data they capture, they're being ordered based on not only variance, but also like how separated the two classes are. So PLSDA not only gives you scores and loadings, but it also predicts the value of each spectrum. So it predicts what class each spectrum will fall into. So if you feed it a spectrum, it'll try to guess whether it's a 0 gray spectrum or if it's a 5 gray spectrum. If you hover your mouse over the model here, you can see it gives some information, and it won't let me hover my mouse over the information, but anyway, you can see sensitivity and specificity. So the first sensitivity and specificity have a cal next to it, so that stands for calibration. So that's basically predicting the classes of data that was used to build the model. Whereas the sensitivity and specificity with the CV next to it, which stands for cross-validation, is a bit of a better way of judging how good your model is at discriminating between classes, because what it does is it uses different cross-validation techniques, such as leaving one spectrum out and creating the model with all the rest of the data, and then trying to guess the class of the spectrum that was left out. And since we've fed the information of what class each spectrum is, it's able to verify if it was correct or incorrect in its guess, and then you can see basically the accuracy, how accurate the model is by looking at the sensitivity and specificity. So here we have ones, basically means we have 100% accuracy. Before we look at any scores or predictions or loadings though, we want to check if we've used the right number of latent variables. So right now, PLSDA has decided to go for 3 latent variables, but like I showed in the previous video, you can alter how many latent variables you want to store in the model. And while in PCA, it doesn't matter too much how many you decide to keep, because you can always just change which principal components you're looking at in your scores. It actually does matter for PLSDA because depending on how many latent variables you decide to keep, it will affect the accuracy of the predictions. So to check how many latent variables you'd want to keep, you want to head over to this icon right here with the lambda. And that will open this figure along with the plot controls on the left. So what we want to look for is the RMS ECV. So if I click on RMS ECV1, that's telling you kind of the error in the predictions when guessing for class 1. So the first class pretty much. In our case, class 1 corresponds to the 0 gray. So the lower the error, the better. And you also want to keep as few latent variables as possible. So on the x-axis, we have the number of latent variables we're keeping, and on the y-axis, we kind of have the error of the cross-validation predictions. So you want to choose a point that's as low as possible, but also keeps the least amount of latent variables as possible. So a rule of thumb is kind of just to find where it plateaus and choose the number of latent variables right at that point. So in this case, it sort of plateaus at around 3. So the best number to choose would be to keep around 3 latent variables. And that's exactly what PLSDA opted for. So this is a good choice. I'm not going to change it. Next, I'm going to click on the Erlenmeyer flask here to look at the scores and predictions. We get these 2 plots right here. In the first subplot, we have the hotelling t-square and q residual values. Again, this can be useful for detecting outliers. And then in the second subplot, we have the predictions. So if you read on the y-axis, we see y CV predicted 1. So what this means is it's predicting the y value or the class of each spectrum, and it's predicting for class 1. So in our case, class 1 is 0 gray. So what happens is any spectra that fall above this red line is classified as class 1, 0 gray. And any spectrum that falls below is classified as not class 1. So a good thing to do would be to insert a legend just so we remind ourselves which points are class 1 and which points are class 6. And we'll see that the class 1 spectra are all the red diamonds and the yellow circles are class 6. So it looks like we have a perfect discrimination here because all the class 1 fall above the red line. If we want to look at the scores, we just need to double click on one of the spectra, bring over the plot controls, and we just want to change what we're displaying on the X and Y axis. So right now we have sample on the X-axis and the predicted values on the Y-axis. Instead, I want to look at the scores in 2 dimensions. So on the X-axis, I'm going to put scores on LV1. And on the Y-axis, I'm going to put scores on LV2. I'm going to remove the confidence limits. And I will also put some confidence ellipses around our values. I'll put a legend just because it's good practice. And there we go. We have a nice scores plot. We see the class 1 or 0 grade data separated nicely from the class 6 or 5 grade data. You can also look at other scores or other latent variables by choosing them on the plot controls. So for example, we can put LV3 scores on the y-axis. That's what that looks like. We have a bit worse of a separation now because LV3 is not as important as LV2 when it comes to discriminating between the 2 classes or the 2 doses. It seems like the model is also pretty good at separating them only along LV1. So what we can do is look at it in 1 dimension by plotting sample number on the x-axis and then plotting LV1 on the y-axis. Get rid of the confidence ellipse, and we'll see that all of our 0 gray samples have a lower score compared to all of the 5 gray samples, which is very nice. Next, I want to look at the loadings vector to see which Raman shifts are important when it comes to discriminating between the 2 doses. So I'm going to close out of this and just keep in mind that it seems like LV1 is the most important variable when it comes to discriminating between doses because we have a nice separation for LV1, but when we take a look at LV2, there's not much of a separation on the y-axis. Same with LV3. So I'm going to focus on the loadings vector for LV1. I'll close out of those and then hit this button right here to open the loadings. So this is what we get. We have LV1 on the y-axis, so the loadings vector, and then on the x-axis we have the variable number. So it's kind of like the column number. It's not actually Raman shift at the moment. If you want to look at the LV2 loadings, just click on LV2 here. We'll see it's a bit noisier and seems a bit more random than LV1 was. And then if we want to look at LV3, just click on LV3 and we get even noisier. And that's how you look at loadings vectors in PLSDA. Since PLSDA is used to predict the classes of different spectra, we can also bring in our test data to see how well it performs on data that was not used to build the model. Now, the first time we imported data, we imported data into the X and the Y block. PLS Toolbox, however, is nice because if you only load data from the X block, so I'm going to bring in the test data. I'm going to go to Edit. And basically, it'll recognize the class as your Y vector if you don't specify a Y vector. So we want to specify a Y vector, which includes the class of the spectra, just so we can know if our predictions are accurate or not. And all you have to do that is just select the second column here, which includes our class, and say use as class. And if you do that, you don't have to enter data into the Y block separately. So that's kind of the best way to do it, I think. I just wanted to show you how to do it the first way, just so you understand that in PLSDA, you're not only feeding it intensities, but you also have to feed it the class of each spectrum. So I'll hit OK. And again, we just want to get rid of these 2 columns. So I'll right click and exclude selected. Once that is done, we'll X out of that and apply the model by pressing on the orange button. Once that's done, we can hover our mouse over this orange button And we now see the sensitivity and the specificity of the predictions. So we have two ones there, which means we have a 100% accuracy. And by the way, each column of ones here is actually representing the sensitivity or specificity of predicting for one of the classes. So I believe the first column corresponds to the sensitivity or specificity of predicting the class 1, so our 0 grade data, and our second column corresponds to the sensitivity or specificity of predicting the class 6 data, which is our 5 grade data. So it seems we have a 100% accuracy, so that's good. We can click on the Erlenmeyer flask again. This time, instead of showing us our predictions and scores for the data that was used to build the model, we're only looking at the test data instead. So you can see all of our red data falls above the red line, which is great, and all of the yellow data is below the red line. So that's perfect. That's a 100% accuracy right there. We can double click on the plot again to bring up a second figure. And then over here, we can change the axes to show LV1 and LV2. Get rid of the confidence limits and apply the confidence ellipse. With the confidence ellipses, it looks like the separation is not as nice as it was before, but we just have less data, so the confidence is a bit, the confidence ellipses are a bit wider. But looking along LV1, there is a perfect separation here. So if I get rid of the confidence ellipses, plot sample number on the x-axis and then LV1 on the y-axis, we see that the yellow data is perfectly separated from the red data. And that's exactly what we want. We can look at the loadings vector again, but it's not going to change. The loadings vector only depends on the data that was used to build the model. So I'm going to do just one more quick example, because so far we've only been looking at 0 versus 5 grade data, but you can have more than just two classes within your data set. So what I've done is I've imported the data from donor 19, and I've got all the doses, 0, 1, 2, and 5 gray, all the serial numbers, and all the same pre-processing that we had before. So this time what I'm going to do is load the X data. I'm not going to go into the Y data for the reasons I just showed previously. I'm going to hit Edit. I'm going to use the second column as class. Hit OK, and then exclude the first two columns. So now you can see we have red for class 1, which is our 0 grade data. We have green for class 2, which is our 1 grade data. Blue for class 3, which is our 2 grade data. And it looks like green for class 6 here, which is our 5 grade data. But we'll see when we actually plot, it's not going to be the same color as class 2 over here. So close out of that, choose mean centering, and build the model. I'm going to check the RMS ECV values to make sure PLSDA chose an appropriate number of latent variables to keep. So I'll put RMS ECV1. I'll also plot RMS ECV2 by holding Control and selecting it, and all the other ones, RMS ECV4. So all these numbers correspond to the error for predictions of the corresponding class. So the first class is our 0 gray, second class is our 1 gray, third class is our 2 gray, and fourth class is our 5 gray. So essentially you want to look at all of these RMS ECV values or curves and try to find the point where they all start to plateau. So I'm seeing that around 5 latent variables is where this purple curve starts to plateau. It doesn't really change its value too much. So 5 seems to be a good number for this one. 4 seems to be a bit of a better number for this blue curve. 5 seems to be an okay number for the yellow curve, and 5 is also all right for the orange curve. For the orange curve, though, I would probably, if I could, I would rather choose maybe 6 or even 8. PLSDA opted for 4, as we can see here. which I guess might be okay, but what I'm going to do is I'm going to change it to 5. So I'm going to click on the 5th row and then hit the model button again, and that's done. Hovering over the model button, we can see the sensitivity and specificity for the calibration data and cross-validation results. As we can see for the cross-validation results, we have kind of worse results than for the calibration model, which makes sense. We can hit the Erlenmeyer flask to look at the results visually. So now we have a lot more plots, and that's because we have 2 more classes that we're trying to predict for. So I'm going to open this in full screen. So you just want to pay attention to the y-axis label so you know what that specific plot is trying to predict. So in this case, it's trying to predict for the first class, so that's the one there, and our first class is class 1, our 0 gray data. So everything above the red line, it's classifying as 0 gray. So in this case, it seems to have got most of the red diamonds above the red line, so that's good. And it got very few of the other doses above the red line. So not too many misclassifications, but it's not perfect as it was when we only used 0 gray and 5 gray. In this second subplot here, we're predicting for the second class, which happens to be class 2. Everything above the red line is being classified as 1 gray, and our 1 gray data are these green points. So ideally what we should be seeing is the red, blue, and yellow data fall below the red line, but all the green points to fall above the red line. And that's not what we're seeing, so we're not getting a very good prediction accuracy for the 1 gray data here. Same idea for this third subplot. We're predicting for the third class, which is class 3, our 2 gray data. That's the blue set right here. So it seems like most of them are above the red line, so that's good. But some of them are being misclassified as not 2 gray. And we have a few other misclassifications for the other spectra. So it's not too bad, but it could be better. Finally, in the last subplot, we're predicting for the fourth class, which is class 6, our 5 gray data. So everything above the red line is being classified as 5 gray. As you can see, all of our 5 gray data has been classified perfectly, so that's good. But seems like we have two gray spectra that have been misclassified as 5 gray data. So this seems to be actually very good accuracy right here. Another thing we can do is just double click on one of these plots to bring it up in its own figure. And then we can look at the scores again. So on the x-axis, I'll put LV1, and on the y-axis, I'll put LV2. We'll get rid of the confidence limits. And I think if we add the confidence ellipses, it's not going to look too great. Yeah, it's a little messy, so I'm going to get rid of that. But that's what the scores plot now looks like. So LV1 on the x-axis, LV2 on the y-axis. There seems to be a nice separation between the 0 gray data here and the 5 gray data here, so the red and the yellow points. It seems also like there is a separation between all the doses really, because in this area it's dominated by the red, this area is dominated by the green, here it's the blue, and then here it's the yellow. So the nice thing is it also seems to be kind of a trend here. So we're going from 0 gray to 1 gray to 2 gray to 5 gray, which is what we would hope to be seeing really. So just to remind ourselves, insert a legend. We'll see the red is 0 gray, green is 1 gray, blue is 2 gray, and yellow is 5 gray. So this is actually quite a nice scores plot we have here. So that's about it for PLS-DA. It's very similar to what we did with PCA, but the main difference is just that we can actually predict the class of unknown samples, and that's the power of PLS-DA. And just remember that along these latent variables, so when we were doing PCA, we were seeing scores on PC1 and PC2 instead, so those were called principal components. In PLS-DA's case though, these are called latent variables. So along the latent variables, unlike principal components, we're not only trying to maximize variance, but we're also going in the direction of maximal separation between different classes.